Everybody, thank you for being here at this IJCNN conference. I'm very happy to try out this new format. I'm Henri de Plan at EZ Studies at KU Leuven in Belgium. And I'm very happy to present you our newest paper, jointly written with Michael Fanuel and Johan Serkens. Without further ado, Wasserstein exponential kernels. In the context of kernel methods, one of the most popular kernel is the RBF kernel. It measures a similarity, like every kernel, assigning to 1 data points that are very close to each other, and assigning to 0 data points that are very far from each other. But the question is, how do we measure this distance? Classical RBF kernel uses the L2 distance. The problem of this L2 distance is that it doesn't take into account the underlying structure of the data. I'll show you with an example. Let's consider the distance between those two images. The pixels are not on top of each other, and so the total Euclidean distance is 2. If we consider a variation of this problem with a pixel slightly off, then the Euclidean distance will still be 2. The only way to have a distance different than 2 is to have the 2 pixels on top of each other, and the distance will be 0. This phenomenon actually is one of the weaknesses of the L2 distance. It only measures the strict correspondence of the pixels with each other and doesn't take any sense of neighborhood into account. This sense of neighborhood is, for example, one of the advantages of convolutional neural networks. So now there is a question: can we find a measure that takes this underlying structure into account? And in fact we can, and this introduces us to optimal transport. So I'll go very fast over optimal transport, and sorry for the people who don't have an introduction, but I'll still go through a very fast introduction. The idea of Monge's problem, who is the father of the optimal transport, is to transport one pile of dirt onto another one, and to look at all possible transport maps, which we call push-forward operators, and find the one which minimizes the cost. The problem is that it's not always well defined, for example, in this problem. And more generally, every time you have to split one element into different ones, you have a not well-defined problem. This was solved by Kantorovich in 1939 by not considering a transport map anymore, but joint distribution. And you can also redefine the cost associated with this joint distribution. But much more interesting than this transport map or joint distribution is actually the cost itself, because the cost itself defines a distance, which is the Wasserstein distance, and is the one that we are going to consider now. In practice, this is a linear problem, but there exists actually a much more efficient way to solve that problem, and we have to consider a slight variation of the problem, which is the regularized Wasserstein distance, where we add a regularization term. This can be easily computed with an algorithm which is called Sinkhorn's algorithm, and is also very scalable, as it can compute the distance of one element to a whole bunch of different elements together using GPU parallelization. Now that we have defined a distance which takes into account the underlying structure and a way to compute it, we can define our new kernel function by just changing the L2 distance by the Wasserstein distance. And to illustrate this, we can consider a specific case of Wasserstein distances where the data points can be ordered, so are one-dimensional, and we have an equivalence with an LP distance. But those only holds for one-dimensional. So if we really want to take the underlying structure into account, we have to consider higher dimensions. However, there is a slight subtlety. This kernel is not positive definite. As a reminder, a positive semi-definite kernel is a kernel where whatever the kernel matrix you build, this kernel matrix will always be positive semi-definite and equivalently have only positive eigenvalues. And this property is central to reproducing kernel Hilbert spaces, which is at the center of kernel theory. One of the theorems that does not apply anymore is the representer theorem. This states that if you minimize a certain regularization functional in a specific, maybe infinite dimensional, reproducing kernel Hilbert space, then the solution will lie in a finite dimensional subspace, spanned by the representers of the data. This means that the complex nonlinear problem reduces to the search for a finite number of coefficients. If you do not have positive semi-definite kernels, then all these theorems are not applicable anymore. For example, the representer theorem only applies in the quest of the saddle point of this regularization functional and not its minimum anymore. So you lose quite much of the interpretation and of the theory. But the question we can ask ourselves is, now that we know that there are kernel matrices with possibly negative eigenvalues, how negative are these eigenvalues? What information do they contain? And can we possibly drop them? Well, we have shown a small result that shows that there always exists some interval of bandwidth that leads to positive semi-definite kernel matrix. And the idea to prove this is quite simple. You just have to show that in the limit to 0, you will get a kernel matrix, which will be the identity matrix. So all the eigenvalues will be 1, including the smallest one. And in the limit to infinity, you will get a kernel matrix only consisting of 1s. By consequence, the biggest eigenvalue will be the dimension of the kernel matrix, and all the others 0, including the smallest one. And if you can also show that the eigenvalues are continuous in function of the bandwidth, then you get that there is a crossing point. And all the values of bandwidth is smaller than this crossing point will lead to positive semi-definite kernel matrices. Now, does this interval make sense? Is it leading to meaningful bandwidths? So here you can compare the RBF kernel and our Wasserstein exponential kernel for a certain bandwidth. It's based on the MNIST dataset and they are ordered in ascending order. So ideally we would have to want only blocks on the diagonal and all the rest blue. And you can already see visually that the Wasserstein exponential kernel matrix may contain, only visually at least, more information than the RBF kernel. And you can also see that our bandwidth choice leads to only positive eigenvalues. So it seems to lie in this interval that we have theorized the existence in the previous proposition. But what this proposition also suggests is that if you have still negative eigenvalues and you are sufficiently close to that crossing point, then these negative eigenvalues will be very small proportionally in magnitude. So you could also drop them, they won't contain so much information. And this leads us to the Wasserstein features. The idea of Wasserstein features is not only constructing positive semi-definite kernels by definition, but also allowing to do out-of-sample extensions, allowing to reduce the computation cost. And the way it works is actually quite simple. It's just by computing the eigendecomposition of the kernel matrix based on, let's say, a core set, and to truncate it by dropping the negative eigenvalues, which you will know will be small in magnitude. And based on that, you can build the Wasserstein features for new data points that are spanned by the remaining eigenvectors of the kernel matrix, and the coefficients are based on the distances to the core set. And you can see that this definition is consistent, because if you compute the out-of-sample extension on the core set, then you will result back in the truncated kernel matrix. We can look now also at the complexity of computing these Wasserstein features. Because distances are symmetric, you only have to compute the upper triangle of the kernel matrix. And furthermore, you can also artificially put the diagonal equal to distance 0, so kernel 1. So if you choose a core set, you can, for example, choose only a subset of this kernel matrix, and you will have a core set of a certain size. Then to compute the out-of-sample extension, you will need the coefficients to span this subspace, and this will be here blue, and the out-of-sample extension will give you the rest of the upper triangle. Another advantage of the Wasserstein features is to use it together with synchronous algorithm. So, as we said before, synchronous algorithm is able to compute the distance of one element with a whole bunch of other elements in one time. In other words, compute a full line of the matrix in one time using parallelization and GPU capabilities. This means that you can compute the green part of the kernel, the core set, and the blue one, the out of samples, in one time. So we would only have to compute 4 lines on the 17 on the left matrix and 7 lines on the 17 on the right matrix, instead of computing it whole. And that is really the big advantage. I mean, the big synergy between synchronous algorithm and the out of sample extension of the Wasserstein features. Now, how many features do you need to make a consistent and a sufficiently good approximation? Well, I'll first show you a graphical example. So here's an example where we have used 500 data points in the core set, and we are estimating 500 other data points, and we can compute the Wasserstein exponential kernel on the left and the L2 kernel, the RBF kernel on the right, and this is based only on 5 features. And now we can increase them, and we see 10, 50, 250, and 500. And you can actually see that you don't need so much features to have a consistent approximation, at least graphically. But now we have seen all of that graphically, let's have a look at the real performance. To test our kernel, we have built a simple setup based on least square support vector machines. Least square support vector machines are just a variation of classical support vector machines, Vapnik's support vector machine, where you replace the inequality by an equality and you introduce a least square problem. To solve this, you just have to solve a linear problem, which will be of the dimension of the feature space. But also, like in support vector machines, you have a dual problem, which will depend on the size of the data points, of the size of the kernel matrix. And you see here coefficient alpha, which corresponds to the coefficient in the representer theorem. And as you see, we only have linear problems to solve, so technically we can also put some indefinite kernel matrix. And this will actually lead, as for the representer theorem, to solving saddle point of the objective function and not to finding its minimum. So we can also test it with the full kernel matrix and with the negative eigenvalue still in it. But just before the results, we would also like to introduce a little variation we introduced. It's called the reweighted kernel, and it's based on the idea that not all digits have the same amount of ink, if I can say, the number of pixels that are colored. And to compute the optimal transport distance, we had to normalize, so suppress that information. So we can reintroduce them by introducing a variation of that kernel by multiplying the kernel by the total number of ink, the one norm actually, of both elements. As a reference for the experiments, we also computed the nearest neighbors, both with the Wasserstein and with the Euclidean distance. And as you can see, the Wasserstein method performs better, that is the purple line, but performs better than the Euclidean version of the nearest neighbors. And for kernel methods, also the Wasserstein distances seems to perform better than the Euclidean distances. You can first see that the outer sample extension, which reduces drastically the computation time, doesn't perform much worse than its full version. And you can also see that the indefinite kernel version of the kernel, without suppressing the negative eigenvalues, performs in a very similar way for small datasets, but as the dataset increases, then it still performs better. This means that suppressing the negative eigenvalues first doesn't have a lot of influence, but as the dimension of the training set augments, and thus the amount of information, these negative eigenvalues still seem to add some additional information. You can also see that the reweighted Wasserstein kernel and its non-reweighted version perform in a very similar way. The big advantage of our kernel is also on small datasets. On small datasets, the computation time is not so relevant, or at least is much less relevant, and you perform much better than methods that are typically considered as state-of-the-art in kernel methods. So in small datasets on shapes, this method seems to have a significant advantage. Here are the results on more datasets. So you have the MNIST dataset, which we just have saw, the QuickDraw dataset, which is provided by Google, which consists of shapes that are a little bit more complicated than the digits of various objects, buildings, people, actions, and then the USPS digit dataset. And you can here again see that the Wasserstein kernels perform in general much better than the RBF, classical RBF kernel. So we now come to the end of our presentation. So in conclusion, to summarize what we have shown, is that the Wasserstein exponential kernel performs quite well on small datasets consisting of shapes. We have also shown that you can construct to reduce the computation time an out-of-sample extension. And this is supported by our little theoretical results that shows that for a good choice of bandwidth, the negative eigenvalues can be negligible. But this theoretical results doesn't actually only apply to Wasserstein distances, but to any distance or even pseudo-distance or maybe heuristics. And that's interesting because it opens a door to other kernels based on other distances. And I'm actually very curious to see what we are able to do with that. So Thank you all for listening and have a good evening.